Well, hi everyone, this is Bob the Science Guy. I had so much fun listening to Dave Weiss, DRTH, the other day, arguing with ChatGPT, I decided to do it again. Now, today's subject is going to be gas pressure in the atmosphere next to the vacuum of space. And what Dave is going to do is he's going to get ChatGPT on the line and ask it this innocuous question. If I have a can of soda here and I open the top, I get a rush of gas that comes out because the gas in the soda can is pressurized compared to the gas in the atmosphere around it. Now, this is a very classic flat Earth argument that we've heard many times before. It's one of the classic 2015 arguments they keep going back to on their memes. Dave is going to try and get ChatGPT to agree with him that it's not possible to have a quote-unquote pressurized gas system next to the vacuum of space without an intermediate dome. Now, of course, we do realize why we do have atmospheric pressure. We realize why we have an atmospheric pressure gradient, and we realize why it's not a big deal to continue that gradient up to the vacuum of space. But let's see Dave try and work his way out of this.
I have some questions about air pressure. Can you help me?
Of course. I'm happy to help. What specifically would you like to know about air pressure?
So when you open up a can of a carbonated drink, it makes a psst noise. That's because the air pressure in the can is greater than the air pressure in the room. Is that correct?
Exactly. Inside the can, the liquid is under pressure from dissolved carbon dioxide. When you open the can, that pressure is released, causing the gas to escape rapidly and making that characteristic psh sound. The pressure inside the can is indeed higher than the atmospheric pressure in the room.
If the air pressure in the room, just for demonstration purposes, if the air pressure in the room was equal to the high air pressure in the can, when you open the can, there would be no exchange of gases. Is that correct?
Yes, exactly. If the air pressure in the room matched the pressure inside the can, there wouldn't be a pressure difference to drive the gas out. In that scenario, the gas would stay put, and you wouldn't get that psh sound at all.
Okay, so let's go ahead and unpack this so far. We've got three very important points to go over that Dave has brought out and demonstrated. The first one is that when we have a can of soda, where we have carbon dioxide gas under high pressure in the can, and we crack the top of the can and release that high pressure into the lower pressure of the surrounding atmosphere, you'll get a rapid transfer of the gas that's in the can out to the atmosphere until the pressure equalizes. Okay, that's fine. Absolutely agree with that. Second, and Dave was very clear to mention this, is when you raise the pressure in the room to equal the pressure of the gas in the can. If you were to open it under those conditions, there would be no exchange of gas because there is no pressure difference between the gas in the can and the gas in the room. And the third thing that I want to point out is the debate style that Dave is using with ChatGPT, which, as you well know, is not human. It is a machine. It doesn't get intimidated, and it doesn't pick up on nuances of things that he says. But one thing that it will do is when Dave asks a question and it starts to answer that question, he listens to the part that he wants to hear and then immediately stops ChatGPT from going on and discussing anything further. This is characteristic number one of science denial, and that is cherry picking. What he wants to do is he's looking for very specific answers, and he doesn't want to hear anything to the contrary of those very specific answers. And that's why he's stopping ChatGPT. You'll see this in live debates as well, between Globers and science deniers. They will ask a question, the Glober will go ahead and start to answer the question, and as soon as the information that Glober is putting out becomes inconvenient to the flat earther, they'll immediately interrupt and try and derail the conversation and prevent him or her from getting that information out. Dave is actually trying this tactic on ChatGPT, which I find very amusing. Let's listen to a little bit more.
All right, next question is, what if we load, so we have let's just say the pressure in the can is just whatever it is, normal pressure, and we took the air pressure in the room down 50%. The exchange of air pressure would be more violent because there'd be a greater difference, yes or no?
Yes, that's correct.
All right.
Air pressure in the
So continuing, if we keep lowering the air pressure in the room, the gas will still come out whether we open the can on its side, upside down, right side up. Gravity will play no part in holding the gases in the can, and the lower the air pressure in the room, the greater the discrepancy between the can and the room, the more violently and quicker the exchange will be. Is that correct? Yes or no?
Yes, exactly. The orientation of the can doesn't matter because the gas will rush out to equalize the pressure difference. The lower the air pressure in the room, the more dramatic the release of gas from the can. Gravity doesn't play a role in the gas exchange. It's all about the pressure difference.
Now, once again, what we're hearing here is Dave try to cut ChatGPT off. And he's using another tactic as well, and that is, what is the answer to this, yes or no? All right, he's trying to give ChatGPT options as to how he wants the question answered. And ChatGPT, of course, being a machine and not a person, is just doing its thing. So that's characteristic 1 of science denial, which is cherry picking. Characteristic 4 of science denial is poor deductive reasoning, and we're seeing that in this situation as well. Dave is clearly making the connection that if you increase the pressure gradient between the gas in the can and the gas in the room by lowering the pressure in the room, you're going to get a more violent exchange due to the greater pressure gradient. Now, the other shoe is that if you raise the pressure in the room, you'll get very minimal gas exchange because the pressure gradient is not as much. Now, he's doing this with pressure. He should make the connection that you can do this with a vacuum as well. So if you have a vacuum in a can and you open it, the ambient air pressure in the room will rush into the can to fill that vacuum. However, if you lower the ambient pressure in the room to nearly a vacuum as well, you won't get as much of an exchange because the pressure gradient is very low. Now, obviously, the reason that we don't have all of our atmosphere escaping into space is because we have a pressure gradient in our atmosphere. And as we go higher in the atmosphere, getting closer to space, the atmospheric pressure is also approaching a vacuum. And by the time you get up past the Kármán line, you have a near vacuum pressure in the atmosphere next to a near vacuum pressure in space. There's no pressure gradient anymore. But hey, don't take my word for it. Let's let him continue to talk to ChatGPT. Notice that he did work in gravity into this scenario where he had high pressure gas in a can next to low pressure in a room. He got ChatGPT to say that gravity won't have any effect on the gas escaping from the can. And that, of course, is correct. But he's going to try and parlay this into a point later on. We'll see him do that.
So what about if we lowered the pressure in the can to, let's just say, 1% atmosphere in the can, 1% of what our normal atmosphere is, but we lowered the room to 0. So the room is a vacuum. It would still violently go out. It wouldn't just sit in the can being held down by gravity. It would equalize into the room. Is that correct?
Yes, that's right. Even if the pressure in the can was very low, like 1% of atmospheric pressure, if the room was a vacuum, 0% atmospheric pressure, the gas would still rush out of the can. The key factor is the difference in pressure. As long as there's a pressure difference, the gas will flow from the higher pressure area, the can, to the lower pressure area, the vacuum. Gravity wouldn't stop that. The gas would escape into the vacuum very quickly.
All right, so now let's reverse it. Now I have let's just say I have a box, which is a vacuum. There's no air. It's a zero pressure, zero gas in the box. And I open it up in a room with regular air pressure. No matter where I open it, side, bottom, top, it doesn't matter. The air in the room will violently fill in to equalize. Correct?
Yes, exactly.
All right, so wait, hold on. I don't need a detailed explanation. So if I lower the air pressure in the room down to 1% atmosphere, it's still going to go into the box, right? Gravity's not going to hold it to the floor. The box, whether I hold it near the ceiling or near the floor, whether I open the top, bottom, or side, if there's 1% atmosphere in the room and 0 in the box, the room will equalize and pull up and go into the box. Yes or no?
Yes, absolutely. Even if the room's pressure is only 1% of normal atmosphere, it's still higher than the vacuum inside the box. That difference in pressure will cause the air to move into the box, regardless of orientation. Gravity won't prevent the air from equalizing, so the air will flow into the box, whether it's on the ceiling, the floor, or the side.
And gravity takes no part in holding the air down. It's the pressure that dictates where the air goes, correct?
Correct. It's the pressure difference that dictates how the air moves.
All right.
Gravity does it.
Yeah, so now, sorry to interrupt again, but is there a way I could have a cubic foot of a vacuum inside of a room where I don't have a container for the vacuum? Can that exist?
No, that can't exist. A vacuum is the absence of air. So to maintain a vacuum, you need a physical barrier, like a container, to keep air from rushing in. Without a container, the air in the room will immediately fill that space. So you can't have a cubic foot of vacuum just floating in a room.
Okay, so Dave is doing a masterful job of trying to set up ChatGPT here. A couple of things that I just want to point out. He is putting out an unrealistic scenario where you have a cubic foot of vacuum uncontained in a room full of atmospheric pressure air. Obviously, the atmospheric pressure will rush in and clear out the vacuum and equalize with it. However, what happens if you have a cubic foot of vacuum in a room that has a vacuum? You're not going to get any movement of air because there's no pressure difference. And that is the situation that we're going to see eventually with the atmosphere here. Now, ChatGPT tried to say something about the effect of gravity on the atmosphere. Notice how quickly Dave shut it down. He immediately stopped ChatGPT from carrying on the discussion as soon as the word gravity was mentioned.
What about if we reversed it? If I had a cubic foot of air and the room was a total vacuum, could I have that cubic foot of air without a container?
The air would immediately expand and rush out into the vacuum. Without a container, there's nothing to hold that air together, so it would spread out until the pressure equalized.
What if I had that cubic foot of air down on the ground in this vacuum area, this vacuum room, but no container, but it was down near the ground where gravity is the strongest? Would that help?
No, it wouldn't help. Even near the ground, gravity isn't strong enough to keep a pocket of air together in a vacuum. The air molecules would disperse almost instantly to fill the vacuum. There's no way to keep that cubic foot of air intact without a physical barrier in a vacuum environment.
Okay, now I'm going to review a few of the things that you said and then ask you a question, and I want you to answer them scientifically, without consensus, without reading Wikipedia. I want you to answer them scientifically.
Did Dave just threaten ChatGPT and tell it that it couldn't use certain sources, or that it had to employ independent thought outside of science to answer his question? That's an interesting approach, Dave. You know ChatGPT is not a person, right? I need to check that.
So you said gas needs to be contained, needs a container. Gravity does not affect the direction gas goes. It's the pressure difference that dictates where the gas goes. If we had 1% atmosphere and 0, they would equalize up, down, left, or right. You agree with that, and you said gas needs a container, or a vacuum needs to be contained if it's surrounded by gas. So we've determined all of that.
All right. So let's go for the money shot here. Let's go see what Dave really wanted to talk to ChatGPT about.
So the Earth, we're told, is a globe surrounded by high pressure air adjacent to the void/vacuum of space. How come the air doesn't equalize into space?
That's a big and interesting question. In the standard scientific model, Earth's atmosphere is held in place by gravity.
Stop. You said gravity does not hold air down, and at high altitudes, the gravity is even less than it is on ground. How could the gravity not pull the air into space? You can tell me you don't know and it's an anomaly and you don't have an answer, but don't lie.
I understand what you're getting at. Gravity does hold the atmosphere to Earth. Even though gravity decreases slightly with altitude, it's still strong enough to keep the atmosphere from escaping into space. The atmosphere gradually thins out with altitude, creating a pressure gradient. This is why we have a thick atmosphere at the surface and it becomes very thin at higher altitudes.
I understand why you say that there's a pressure gradient. That's why I asked you earlier if the room had 1% atmosphere, which would represent the very top of our pressure gradient adjacent to a void. If I had a box that represented outer space, which is a vacuum, you said no matter what, the air would equalize up and away from gravity into it. But now you're claiming that gravity holds it down. Do you see the discrepancy here? Do you see what you're doing?
I see your point. The analogy with the room and box is simplified. In reality, Earth's atmosphere is a large, continuous system. Gravity acts on the entire atmosphere, creating a pressure gradient from the surface all the way up to the edge of space. The atmosphere doesn't just sit next to a vacuum, it gradually transitions into it.
So you're telling me now if I took that box of, I have a box of no pressure, of a vacuum, and I brought it up to 10,000 feet and opened it, it would suck air up and away from gravity. If I brought it up to 100,000 feet and opened it, it would suck the air up and away from gravity. If I took it to the very top of the atmosphere, all of a sudden it would stop equalizing, because earlier you said no matter what, if there's any difference in pressure, the pressure will equalize. Don't make up shit when you're answering.
Did poor Dave just swear at the computer? I think he did. He's really starting to get frustrated if he's yelling at a machine. The machine's not going to be intimidated by you, Dave. It's not going to play by your rules. Yes, you laid out some very careful scenarios, and the computer actually saw through what you were doing. Yes, if you have a vacuum at sea level and open it, air pressure will rush in and equalize. If you do it at 10,000 feet or 100,000 feet, the same thing will happen because the atmospheric pressure at those levels is higher than a vacuum. However, when you get up to the top of the atmosphere, atmospheric pressure there is a vacuum. And if you open a vacuum in a vacuum, you just have more vacuum. That's why gravity contains the atmosphere against the vacuum of space by creating a pressure gradient that goes from sea level all the way up to a vacuum. Now, just for laughs, I went ahead and looked up the atmospheric pressure at 420 kilometers above the surface where the ISS is. And then I went ahead and calculated at what height, using our pressure gradient model of our atmosphere, would the atmospheric pressure be equal to what it was at the ISS. And here's what I got. Now, atmospheric pressure at the level of the ISS is about 1 times 10 to the negative 8 torr. Converted that to kilopascals, did a little bit of math on it, and as you can see, the altitude above the surface of the Earth at which the atmospheric pressure is 1 times 10 to the negative 8 torr is about 171 kilometers. The ISS is at 420 kilometers. Why is there a little bit of a difference here? Why would the pressure gradient of the atmosphere be that level at a lower altitude? It's because there's almost no air up there. And the fact that it doesn't change very much in 150 kilometers from next to nothing to still next to nothing simply is due to the fact that there's nothing there to begin with. But God forbid Dave try and do any math or actually look anything up. Now, basically, that's pretty much what I wanted to accomplish with the scientific aspect of this. Now, let's just listen to Dave argue with ChatGPT for a few minutes.
You're right that the principle of pressure equalization applies at any altitude. If you have a vacuum container and open it, air will move to fill that vacuum regardless of direction. The reason Earth's atmosphere doesn't simply vanish into space is that gravity continuously acts on all the air molecules, keeping them bound to Earth. The atmosphere thins gradually as altitude increases, forming a gradient. But it's not a hard boundary. It's a gradual transition where molecular motion and gravity are in balance. That balance is why the atmosphere doesn't just rush off into space.
You're contradicting what you said earlier. You said no matter what the difference in the vacuum to the pressure in the room, whether it's 1% or even less, that it would equalize. But now you're saying there's a magic line where the vacuum will not equalize. What is that percentage? What percentage atmosphere is it where it will stop equalizing?
There isn't a specific magic line or percentage.
Because you're making it up. That's why there's not a specific magic line. Will you admit that to have air pressure, you need a container because the air needs to push off of something. I could have a tall tank of oxygen or hydrogen or propane, and if it's half full, the bottom will be liquid, the middle will be a thicker gas, the top will be a thinner gas. There's a pressure gradient. And if I made that tank 100 feet tall or 1,000 feet tall, it would get thinner and thinner and thinner. And then if I put a hole in it anywhere, all of the gas would instantly equalize with the outside air, especially if it was in a vacuum. So you need a container to have pressure, and a pressure gradient is necessary to have a container. That's correct, right?
What? A pressure gradient can form naturally due to gravity without.
What would it be pushing off of? What would the pressure needs to be pushing off of its container? What is the pressure of the atmosphere pushing off of? And if you say gravity, you're a liar.
In the atmosphere, the pressure at any point is due to the weight of the air above it. Each layer of air is compressed by the layers above it, creating a pressure gradient. That gradient is a result of the gravitational pull acting on the entire.
You said that gravity does not affect the gas at all. It has to do with pressure. But now you're invoking that gravity on a large scale does hold gas down, where we can physically demonstrate with boxes of air and boxes of vacuums that gravity takes no part in it. But on a planetary scale, all of a sudden the rules change?
I understand the confusion.
There's no confusion here. You're just making up crap to defend the globe model.
I swear to God, these things write themselves. So once again, we saw Dave get into an argument with an inanimate object, lose, get mad, and then declare victory. So this is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by. These things are a lot of fun to do. They literally write themselves. And he's got several more of them that I'm going to be looking at, some of which actually contain 2 or 3 episodes worth of stuff. So until then, I'll see you again soon. Take care, everyone.